Hi, welcome to AP Physics C, Unit 5. In this first video, we're going to discuss torque and rotational statics. There's not too much of a difference between an algebra-based course and a calculus-based course. It's just that we introduce in this idea of a cross product, which is a mathematical function in a way to multiply vectors where you actually end up with a vector in return. Okay, so torque, in this unit, what we're going to see a lot is a connection back to some linear quantities. Okay, so we're going to be rotating the objects. So torque is the rotational analog of force. So it's equivalent to the linear force. So what happens is a torque or a net torque will cause objects to rotate around its center of mass. And this is where we bring in the cross product. Okay, so a cross product is a way to multiply two vectors and you actually get a vector in return. And so simply torque is the cross product of the radius or the lever arm and the force applied to that radius or lever arm. So torque is given the symbol tau, and it's R cross F. Okay, now what does that really mean mathematically? Well, it's RF cosine theta. The way torque acts is it acts perpendicular. So for example, in our wrench here, our lever arm is the length of the wrench, right? And then the mechanic is applying a force, okay, to turn it, right? He's really turning. It's more of a three-dimensional flat, right? So he's gonna apply that force along that lever arm, and he's going to get a torque. Now, what do you need to know is that ways to increase the torque. So if I want to increase my torque, I can do one of two things. Right? It's directly proportional to that length, right, of the radius, and it's also directly proportional to the force. So you can do one of two things. You can either increase the length over which that force is acting, or you can simply increase the force. Now, this is also, so the idea of a cross product, this is where you get the statement righty-tighty, lefty-loosey, because what happens is you would use a right-hand rule. You point your fingers in the direction of the lever arm, the radius, and then you curl your fingers in the direction of the force, right? So if I'm looking at that picture of the mechanic, lever arm, force, right? So lever arm is going to go along towards the axis of rotation where the bolt is or the nut is, and then I'm going to cross my fingers, right, into that. The crossing represents the force, and then that gives me the direction that the thumb points in the direction of the torque. So if I do righty-tighty, lefty-loosey, right, I'm going to take my wrench, screwdriver, whatever, right, and if I want to go righty, right, I'm going so I would cross it, right, where my fingers would turn to the right, and know that my thumb points down, so that means it's going to go down, so it's going to tighten it. And if I go to the left, right, my thumb's going to point up, which means I'm going to loosen it. Okay. Now, something you see here is that we talk about statics here. So we have to bring in those conditions of static equilibrium. And so the first condition of static equilibrium goes way back to Newton's laws, right? So it just simply states that the sum of the forces is equal to 0. But we add in a second condition for static equilibrium, which states that the sum of the torques is also equal to 0. Okay. And something that you're going to see pop up here now is something called the moment of inertia, or something called rotational inertia. And essentially, it's like mass. It's the rotational equivalent to mass. It's just resistance to changes in rotation. Now, what happens is the sum of all the tiny points of mass times the radius squared of an object. So you have a couple ways to calculate it. The first one is just simply to do the sum of mr squared, right? So if I have a bunch of if I have a point system, it's just the sum of the mass times the radius squared, okay? But you do have to identify where the axis of rotation is, because remember, if we have r involved, the distance involved, that means that we have to establish a 0 point, which actually may cancel out one of those terms, right? The second way you can do it is to use calculus. And so it's kind of along the same way. It has that mr squared look to it, but you can see it's an integral, right? From R0 to R, right? Or sometimes we call it LX, whatever you want to call R, but we try to stay in the same notation with torque. And then the last way you can see down here is if you have something that's not about, like say the center of mass, or an easy way to calculate it, you can use what is called the parallel axis theorem. And the parallel axis theorem just simply says that the torque, or excuse me, the moment of inertia is the moment about the center of mass plus mr squared, right? And so m would be the mass, and again, r would be the distance from the axis of rotation. Okay, so now let's look at a couple examples. One to calculate the rotational inertia, and the other to do, kind of one of these static equilibrium questions. So here we want to calculate the moment of inertia of a uniform rod about the left end of the rod. Okay, so here we're going to use calculus. So we're going to go the integral from 0 to L of, we're going to call it x, right? Because that's what they call it here. So x squared dm. But the problem again is, see this dm? Well, we have to go back when we talked about center of mass, and remember, establish that lambda is mass over length, but it's also the dm over dl, right? And so that's what we're going to kind of substitute in here. In fact, for this problem, we're going to call it x. So I'm going to take and solve dm lambda dx, just like we did with center of mass, and plug it in there. And so I'm going to say I from 0 to L x squared. Now instead of it being dm, I'm going to say lambda dx. But lambda, again, is a constant, so I can pull that out. So just kind of rewriting down. And now we can take the integral, or we can substitute in this for lambda. So we can say m over L, the integral from 0 to L of x squared dx. And we say that's m over L, and remember, square becomes cubic, so we say x cubed over 3, but we need to evaluate that from 0 to L. The good thing is when you have 0 involved, that second term always kind of goes away, so it's going to be m over L times L cubed over 3, right? And now that, the L in the denominator cancels 1, the L is in the numerator, and so the moment of inertia for a thin rod or uniform rod about one endpoint is 1/3 ml squared. Okay, and you can call it x, you can call that whatever, but that is our moment of inertia about one end. Okay, now let's look at a second problem involving statics. Right, so you have a passenger car with a 2.5 meter wheelbase, has 52% of its weight on the front wheels on level ground as illustrated in the figure, whereas the center of mass of the car located with respect to the rear axle. Okay, so we're going to apply a couple ways you could do this. Is that you can you would apply the you would do a free body, like draw sum solve, right? Free body diagram, sum the forces, and then solve for what you're looking for. But now when we do it here in rotation, you have to sum the torques as well. So I know this is static, so sum of the forces equals 0, sum of the torques equals 0. And I'm going to call my axis of rotation here, because that's where I'm measuring from, right? That's where I want it in regards to. So I'm going to call that my axis of rotation. So if I draw my free body diagram, what forces are acting? Well, even though that's going to be the weight down, they actually act up because we're looking at the support, and then we have the weight down, right? So we call it FR, FL, and then this is FG. So I would have FL plus FR minus FG equals 0. Now, in this question, that's not going to come into play here, but you may have to use this in some way. Now we need to figure out the torque, or the sum of the torques. So my axis of rotation is the wheel from which I'm measuring from. So all my distances will come from that. And then so what that allows us to do is to kind of do, we do our little calculation. We say the torque from the left, sorry, I put an F there. So the torque coming from the left-hand side, right? And that's going to cause Actually, you know what we're going to do? We're going to change up a bit. We're going to go a little kind of, so what we're going to do is we're going to actually call our axis of rotation the center of mass, okay? And then that makes this distance d minus x. So what we can look at is how do these forces cause the car to rotate if they were the only ones acting. And so I would say I have the left torque minus the right torque, because the left one's going to cause it to go positive, right? And then the right one's going to cause it to turn negative. And how do we know that? If you think about the unit circle, right, angles go positive that way and they go negative that way. Down, so up and to the left is our positive angles, down and to the right are our negative angles. And so that our what we say is counterclockwise is positive motion, rotation, clockwise is negative rotation. And so that's what happens. And so you know that these two have to equal each other because it's in static equilibrium. And now we can just start plugging in what we know. So we know that this is going to be RLFL equals R right, F right. Well, my distance from the center, from my axis of rotation is d minus x, and the force is 0.52 W. And then my right-hand side, I've got, it's x away, and then it's 0.48 W. Okay, well, you can see here the W's will cancel out, right? And then I've got some algebra to do here, so I have 0.52 D minus 0.52x, and that's going to equal 0.48x. Well, if I add 0.52x over, well, that's just simply going to be 1. So x is equal to 0.52 times the distance. And so now I can just say x equals 0.52, and the distance is 2.5 meters. And then it's going to be, so it's going to be shifted to 1.3 meters. So not quite halfway, right? It's more towards the front end as expected, because more of the weight is concentrated at the front end than the back end. Okay, so in the next video, we're going to look at rotational kinematics again. So we're gonna do a lot of analogies between Unit 1, Unit 2, Unit 3 up until now.